If we want to to evaluate a double integral, not using a rectangle or even something using rectangular coordinates like a parabola, a line, or a polynomial, but something that's better used to using a circle, then we would want to evaluate our double integral using polar coordinates. So when you have things that are better expressed in circles or things with those polar coordinates, then we're going to use our double integrals in polar coordinates. So before we get started in that, let's review your polar coordinates very quickly. So consider this graph, and this is the pole. This is your xy coordinates, and we have some point up here, xy, and there's a lot that goes into this, but so the point xy can also be written as the point r comma theta, where r is the radius of the circle and theta is the angle that happens here. So this is theta, this would be r, here is your normal x, and here is your y. So we know that x squared plus y squared equals r squared. That comes from a circle, and it works in our polar coordinates here as well. And two notes to make: x equals r cosine theta, and y equals r sine theta. Now, we know that a circle is x squared plus y squared equals r squared, and our unit circle comes in there. And just a little bit about polar coordinates. Let's say that your unit circle, here you have x squared plus y squared equals 1. So then we could say that the region R, let's tie this into this. So R is equal to our polar coordinates r comma theta, such that R is between 0 and 1. The radius is between 0 and 1. Oh, it's shaded in. That's why it's between 0 and 1. It's not just equal to 1. And then the circle is created because theta is between 0 and 2 pi. So you can kind of see the polar coordinates happening there. If we were to look at another one, let's say we have a circle. Here's a radius of 1. We have a semicircle, and here's a radius of 2. So this is all shaded in. So we would say the region here are our points r comma theta, such that the radius is between 1 and 2, and that kind of makes sense if you think about that. And then theta is going to be between 0 and pi because it doesn't complete the whole rotation. So you can kind of see how our polar coordinates are going to come into play as we're doing these integrals. These two pictures that we see here are special cases of what they call a polar rectangle. So a polar rectangle is part of a circle. Let me give you a picture as we talk about it. So here we have a polar rectangle in figure 3, and it's divided into subrectangles in figure 4. But you can see, let's go back to figure 3 real quick. You can see how R is between A and B, and theta is between alpha and beta. So you can see how the boundaries are set up, and we could find the area, the volume under that surface, and when we're working in polar rectangles, and it's divided into subrectangles by figure 4. So if you were supposed to do the midpoint, it wouldn't be too difficult of a task. But let's skip all that and jump into what it looks like for the double integral. So here we have changing to polar coordinates in a double integral. So if f is continuous on a rectangle, and look at this rectangle, R is between A and B, all of them greater than 0, and theta is between alpha and beta, and we know that beta minus alpha is between 0 and 2 pi, so that means that's be positive. Then we can say that the integral, the double integral, is dr d theta. So we have f of r cosine theta, r sine theta, times r dr d theta. This is your x right here, and this is your y. So they're changing it from rectangular to polar. So we're going to look at how this works. but don't forget to put the additional r right here. That's important because it has to do with the area of a sector and the volume underneath of it. So this figure is supposed to help you see that you need the r happening right here for the r d theta, and that's where it comes into play. It has to do with the area that you're working with. So let's go ahead and look at one of these. Now this problem says to evaluate, the word evaluate is up there. We could pretend, but I'll write it in. The double integral of 3x plus 4y squared with respect to the area, where r is the region in the upper half plane bounded by the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. Now, if you think about that, that is what we were talking about earlier. X squared plus y squared equals 1 is a circle that looks like this, the radius of 1, and x squared plus y squared is the radius of 2. So what we have is this area in the upper half plane means we're only looking at the top half of the plane. So here's our x and y planes, and that's what we look like. So let's write our region because that's always helpful. So here we have the set of points x, y, such that you have to define x or y. So we're going to say y is greater than or equal to 0 because that's what gives us the top half of this semicircle. And then I'm going to leave a little bit of space because we have x squared plus y squared. Now, if you look at this, it's bounded by the circles. So the top boundary is 4 and the bottom boundary is 1. So x squared plus y squared has to be between 1 and 4. Do you see that? You say I couldn't dream it up. Well, that's what takes the practice so that you can dream it up. Now, when we get there, the problem is that is not something that we've talked about how to do. So we want to use the formula that we wrote on the previous screen to turn this into polar coordinates because we're working in terms of circles, so polar coordinates would be nice. So let's change this instead to say r is r comma theta. Now let's think about what this means. When we think about the radius is between 1 and 2. So r is between 1 and 2 because we have a radius of 1 and a radius of 2. Now our theta is between 0 and pi because when we switch to theta, when you think in terms of polar, this is 0, this is pi, this is also 2 pi. It's and 2 pi, not divided by. So up in the top you have pi over 2, and the bottom you have 3 pi over 2. So your unit circle helps you build that out. So we can say that theta is between 0 and pi. And I hope that makes sense to you at that point. So now we're going to say the integral. Let's build the double integral. And we're integrating 3x plus 4y squared. That would be our rectangular version. So now we want to turn it into polar. Now when we do that, go back to, I'm going to pull this down just a little bit, and we're going to say that the double integral over r of f of xy with respect to a is equal to the integral from alpha to beta, the integral from a to b, f of r cosine theta, which is your x value, r sine theta, which is your y value, times r, and then we have dr d theta. Alpha to beta are in Greek, so they're going to be in terms of theta. So our alpha to beta would be 0 to pi, and then our a to b is 1 to 2, and our cosine theta, so we're going to say 3 times x is our cosine theta, plus 4 times y is our sine theta, quantity squared, times r, and then we're going to have dr d theta. Well, that's the setup, and that's not too bad. But now let's make it a little more interesting, I guess. 0 to pi, the integral from 1 to 2. So we're going to have 3r squared cosine theta plus 4r to the third sine squared theta dr d theta. So we integrate first with respect to r. That's not too bad. Let's keep the 0 to pi here. So when we integrate 3r squared, we get r to the third cosine of theta plus r to the fourth sine squared of theta. And here I'm going to say r equals 1 to r equals 2 d theta. I don't always write that in, but apparently I'm struggling with keeping track of my variables today. So let me make a good habit for you. So 2 to the third is 8 cosine theta plus 2 to the fourth is 16 sine squared theta minus 1 cosine theta minus 1 sine theta d theta. So we have 0 to pi. 8 minus 1 is 7 cosine theta. 16 minus 1 is 15 sine squared theta with respect to theta. Now, the second one requires, you can't integrate sine squared. Hopefully you remember this from Calc 2. So I'm going to call this 15 times 1/2, and I'm going to use the identity 1 minus cosine 2 theta. D theta. Some books say 1 minus cosine 2 theta all over 2. I would like to split that and pull the 1/2 out front. That's what's going on. If you had me for Calc 2, you know that that's my preference. So you can do that any way you'd like. So we have 0 to pi, 7 cosine theta, plus 15 over 2, minus 15 over 2 cosine 2 theta, d theta. I'm going to make a little note here and do the integration of cosine of 2 theta. I think I'm going to put minus 15 cosine 15 over 2, the integration of cosine of 2 theta, d theta. At this point, some of you do use sub in your head for this, but every time I do, I mess it up. So I'm going to let u be 2 theta, du be 2 d theta. D theta is 1/2 du. So I have negative 15 over 2 times 1/2 the integral of cosine of u du. I put my 1/2 out front, so we're good. So we have negative 15 over 4 times the integral of cosine of u, which is sine of u, plus c. So I have negative 15 over 4 sine of 2 theta. So I'm going to bring these down. So when I integrate 7 cosine theta, we get 7 sine theta plus 15 over 2 theta minus 15 over 4 sine 2 theta. I'm going to put that all on the same line. So we have 7 sine theta plus 15 over 2 theta minus 15 over 4 sine 2 theta, and our bounds are 0 to pi. Double check those bounds. All right, so we have 7 sine of pi plus 15 over 2 pi minus 15 over 4 sine of 2 pi minus 7 sine of 0, not theta, but 0, plus 0, plus 15 over 4 sine of 2 times 0 is 0. Now sine of 0 is 0, so that makes 0. And sine of 2 pi is 0, and sine of pi is 0. So we end up with 15 pi over 2 to be the volume for this problem. I think it just said evaluate the double integral. So that is what you get when you evaluate the double integral. So this one says evaluate the double integral. So it goes from negative 1 to 1 and 0 to the square root of 1 minus x squared. And we have x squared plus y squared dy dx. Now, we want to do it in polar coordinates because that's what we're learning. Could you do it doing rectangular? It might not be pretty, but we're working in polar coordinates, so let's go ahead and do that. If you think about 1 minus x squared, think about the bounds, 1 minus x squared from negative 1 to 1. So if we say y equals the square root of 1 minus x squared and square both sides, y squared equals 1 minus x squared. So x squared plus y squared equals 1. So you have a circle where the x values go from -1 to 1. So you have a half circle that's completely filled in. So you have the top half of the circle. So if you think about this, this would say r is xy such that x is between -1 and 1. And then y is between 0 and that square root. So now let's put this in terms of polar coordinates, because this one's going to be easy in polar coordinates. So we have the points r comma theta. And if you think about r, your radius is 1. So my radius is r is between 0 and 1. And they tend to put theta first. And the reason that they do that is because theta is often usually defined, and if you have an equation, it would be for r. But our theta here is between 0 and pi again, because it is a semicircle, it is a half of a circle, so we're stopping at pi. So we can rewrite this to be the integral. Remember, it's alpha to beta, so it's theta first, alpha to beta, and then a to b. And then we're going to do f of x. Let's say f of r theta. There's not a good notation for me to do that, except to just jump right in. So here we had x squared plus y squared. But remember, let's make a note over here. Remember that x squared plus y squared equals r squared. So since we have x squared and y squared, we can replace that immediately with r squared. And then we have the r that goes on the outside on the right. And then we have dr and d theta. So see how this becomes a nice, really pretty problem when you put it in terms of polar coordinates? So let's go ahead and simplify. We have 0 to pi, 0 to 1, r to the third, dr d theta. So we have 0 to pi. When we integrate this, we get 1/4 r to the fourth, where r goes from 0 to 1 d theta. That's not too bad. I don't think I'll write my r's in. And then we have 0 to pi. So we have 1/4 times 1 minus 0 d theta. 0 to pi, 1/4 d theta. So when we integrate this, we get 1/4 theta from 0 to pi. So this means we have 1/4 times pi minus theta, which is pi over 4. So that is the value of the double integral there. That is the volume of the solid that sits on the surface. And it's not too bad if you consider it that way. This says find the volume of the solid bounded by the plane z equals 0. Pay attention to that. And the paraboloid z equals 1 minus x squared minus y squared. Before we get started into this really deep, let's notice that z equals 1 minus x squared plus y squared. Now remember, x squared plus y squared is r squared, so that's going to help us out. We're going to need that in a little bit. But while we're here, when we plug z equals 0, because z equals 0, we have z equals 1 minus x squared minus y squared. So that means 0 equals 1 minus x squared minus y squared. So x squared plus y squared equals 1. So we know that the paraboloid intersects the circle. So the solid that lies under the paraboloid and above the circle, it's kind of a dome. So it's a really pretty picture. I don't know that I can draw it, but I think I'll try for you. So we're going to go out 1 and out 1 and up 1. So we have we're going back 1 and we're going back 1. And yeah, I'm not going to draw it well. And then it's a dome coming down in that area. So you can kind of see this dome shape. And it's a circle underneath. So think about the fact that we have a circle happening here. And I'm not even going to draw it in 2D. I'm just going to go straight for my polar coordinates. So my volume would have been the volume of the disk of the region of 1 minus x squared minus y squared dA. And let's put that in terms of polar. So here I'm going to call it 1 minus r squared, like we talked about with the r, and dr d theta. Now you have to think about what's happening here. Your radius of this, it's 1 in the x and in the y. So my radius goes from 0 to 1, and our theta goes from 0 to 2 pi because it's a complete circle. So that's not too hard to think about if you can think in terms of your rectangular, if you can think in terms of your polar coordinates pretty well, then this integral is 0 to 2 pi. And we distribute, we still have a double integral here, 0 to 1, because we need to distribute the r minus r to the third dr d theta. Feel like a pirate. So 0 to 2 pi, when we integrate r, we get 1/2 r squared minus 1/4 r to the fourth from 0 to 1 d theta. So we're going to plug in those ones for r. So we have 0 to 2 pi. So I have 1/2 minus 1/4 minus 0. So we have 0 to 2 pi. And 1/2 minus 1/4 is positive 1/4 d theta. Well, that just means we're going to put a theta on it when we integrate. So we get 1/4 theta from 0 to 2 pi. So we get 1/4 times 2 pi minus 0, which is 2 pi over 4, which is pi over 2. So that is the volume of the solid bounded by those shapes. Now, if we had done this in rectangular coordinates, it would be a terrible mess because we would have to do, I'm going to come back over here and just show you. The bounds would be, our bounds from x would be -1 to 1. But our bounds for y would be the square root of 1 minus x squared and the negative version and the positive version. Now I can let you write that out and look at it, but that's a very messy integral. Whereas in the polar, it's because we're working in circles, the polar is a nice and pretty and easy to work with function. Since we've talked about finding the area over a region, now let's talk about finding an area bounded by curves. So if f is continuous on a polar region of the form, notice that our theta is still going to be given bounds, and our r might be in terms of an equation in terms of theta, but that means that these bounds for r are going to change, but nothing else does. So that's important to note and notice. I think I'll leave that notation there. And let's look at how to use that then. So this one says use the double integral to find the area enclosed by one loop of the four-leaved rows r equals cosine 2 theta. Now, if you don't know what this looks like, then grab your graphing calculator, look at your TI-84, hit mode, go to polar mode, make sure you're in radians. I pulled the rookie mistake. I couldn't make it work. Go to your window and set your window from your theta from 0 to 2 pi. Make your step very small, like 0.1. You can make it 1, but you'll have a very boxy instead of a curvy four-leafed clover. So when we're looking at one loop of this four-leafed clover, hopefully your graph looks like mine. I can share a video on how to do this if you need me to. But we're going to look at one loop here. Now, we need to figure out what that is. So if you look at the fact that this loop always goes to 0, then we can say that cosine of 2 theta equals 0. Well, we know that cosine equals 0 when theta equals pi over 2. So at pi over 2 and at 3 pi over 2. So you divide by 2, so you get pi over 4 and 3 pi over 4. So you can use those for your bounds, pi over 4 to 3 pi over 4, but we generally are going to use negative pi over 4 to 4. So we're going to say theta is between pi over 4 and negative pi over 4. Remember that negative pi over 4 and 3 pi over 4 are the same thing. So we tend to use that one because that indicates that we're starting at the bottom and moving to the top and working on this 4-leafed clover. So that's our theta. Let's talk about our r. R is between 0 and cosine 2 theta because it's bounded by that clover, and the clover goes from 0 to cosine of 2 theta, whatever that may be at the time. So that that gives us our region. We're going to say D is r theta. And we tend to write theta first because it's a set value. Theta is between negative pi over 4 and positive pi over 4. And r is between 0 and cosine of 2 theta. And now we could write our integral. So we're going to do a double integral. And when we look at this equation, we don't really have an area given to us except in terms of the equation. So we're just going to say the double integral of dA is equal to the double integral. We'll put a D down here. The double integral, our thetas are negative pi over 4 to positive pi over 4. And our r goes from 0 to cosine of 2 theta. Now when you do this, we've used everything that we're given. Our equation, between the angles and the equation, everything is already given. So often when we do this, the number 1 is going to be here. And there's our extra r, dr, d theta. So lots of times when you have h1 and h2 and you're using this equation with an equation in your bounds, you're going to use a 1 in your double integral. So we're going to say the integral from negative pi over 4 to positive pi over 4. And then I'm going to go ahead and integrate that r to be 1/2 r squared from 0 to cosine of 2 theta d theta. So we have the integral from negative pi over 4 to positive pi over 4. And we have 1/2, and r is cosine of 2 theta squared. So we're going to say cosine squared of 2 theta. And 0 is 0, so I'm going to leave that off and just put d theta here. So I have cosine squared of 2 theta. Now, we're going to use the the half angle identity that we talked about earlier. So we have negative pi over 4 to positive pi over 4. And we have 1/2 times 1/2 parentheses 1 plus cosine 2 theta. But it's 2 theta up here. Cosine of 2 theta is 4 theta d theta. So I'm going to pull out the 1/4, the integral from negative pi over 4 to positive pi over 4. And we have 1 plus cosine of 4 theta d theta. Now, I'm going to do my u sub right here just as a note and then come back to this. So we're going to integrate cosine of 4 theta d theta. We're going to let u be 4 theta. du is 4 d theta. So d theta is 1/4 du. So we have 1/4 times the integral of cosine of u du. Gives me 1/4 sine of u plus c. So we have 1/4 sine of 4 theta plus c. So that means I'm going to come down and I'm going to have 1/4. And when I integrate 1, we get theta. And when we integrate cosine of 4 theta, we get 1/4 sine of 4 theta. And the bounds are negative pi over 4 to positive pi over 4. We don't put the plus c because when you have bounds, the plus c doesn't come into play. So we have 1/4, and then we have pi over 4 plus 1/4 sine of 4 times pi over 4 is pi, minus negative pi over 4, gives me a plus, minus 1/4 sine of negative pi. So we have 1/4. Now sine of pi is 0. Sine of negative pi is 0. So we end up with 1/4 parentheses pi over 4 plus pi over 4. is 2 pi over 4, which is pi over 2. So this answer is pi over 8. Pi over 8. It's beautiful. So that is the area enclosed by one loop of this 4-leaf rose right there. Nicely done. Let's look at one more. Find the volume that lies under the paraboloid z equals x squared plus y squared above the xy plane and inside the cylinder x squared plus y squared equals 2x. So we need to think about what these figures look like. Let's start with x squared plus y squared equals 2x. So that means x squared minus 2x plus y squared equals 0. So I'm going to complete the square. X squared minus 2x plus 1 plus y squared equals 0 plus 1. So x minus 1 squared plus y squared equals 1. So here we have a circle centered at 1, 0, and the radius is 1. So let's put this on an xy plane. Here's 1, 0, and a radius of 1. So we have a circle that looks like this. Mine's a little off. It's okay. And we have that paraboloid z equals x squared plus y squared that's above it, but this is what the boundaries are down below. So this is the important part we need to think about. So let's pause here for a minute and think about the fact that we have this equation, and x squared plus y squared equals r squared, and then we have 2 times x, which is r cosine theta. Now you never divide by your variable, so let's subtract them to the same side. So we have r squared minus 2r cosine theta equals 0. Factor the r, so we get r minus 2 cosine theta equals 0. So r equals 0 and r equals 2 cosine theta. So those are our bounds for r. Isn't that pretty how that worked out? So we're going to say r is between 0 and 2 cosine theta. And that's from that circle right down there. That just gives us that. So we've dealt with this here, but we haven't dealt with the theta part of it. The theta part of it is going to... Now, because of these two equations, we're going to say that cosine theta equals 0, and that means theta equals pi over 2 and negative pi over 2. So that's going to give us our boundaries for cosine of theta. So we're going to say that we have negative pi over 2 and positive pi over 2, and theta is between them. So that gives us our region that we're... Well, that's a colon, not an equals. So we have D, the region, is the set of points r theta, such that negative pi over 2 is less than or equal to theta, which is less than or equal to pi over 2, and 0 is less than or equal to r, which is less than or equal to 2 cosine theta. Now we have not dealt with this up here because we're going to say the double integral of the region of x squared plus y squared with respect to the area is equal to the double integral. Now our bounds for theta are negative pi over 2 to positive pi over 2, and our bounds for r are 0 to 2 cosine of theta. And then we have x squared plus y squared is equal to r squared, and then we have times the extra r, dr d theta. So now we're going to integrate from negative pi over 2 to positive pi over 2. The integral from 0 to 2 cosine of theta. Here we have r to the third dr d theta. I was going to skip that step, but apparently I did it wrong. So let's write it out. When we integrate r to the third, we get 1/4 r to the fourth from 0 to 2 cosine theta. And then when we're done, we're going to integrate with respect to theta. So now we have negative pi over 2 to positive pi over 2. We have 1/4 times 2 to the fourth is 16 cosine to the fourth theta d theta. So 16 times 1/4 is 4, and I'm going to pull that out front. negative pi over 2 to positive pi over 2, cosine to the fourth, theta. Now cosine to the fourth you cannot integrate. So I'm going to go ahead and call this bracket 1/2 parentheses 1 plus cosine of 2 theta, because that's cosine squared, and we're going to square all of that because it's technically cosine squared squared. So that parentheses is cosine squared, and we're going to square that. So we have 4 times the integral of negative pi over 2 to positive pi over 2. 1/2 times 1/2 is 1/4. And then we have 1 plus 2 cosine 2 theta plus cosine squared 2 theta d theta. So the 1/4 and the 4 are going to cancel. We have the integral from negative pi over 2 to positive pi over 2. We have 1 plus 2 cosine 2 theta. And in place of cosine squared, we're going to say 1/2 times 1 plus cosine of 2 times 2 theta is 4 theta d theta. I'm going to distribute this 1/2 up here before I continue on. So we have negative pi over 2 to positive pi over 2. And we have 1 plus 2 cosine 2 theta plus 1/2 plus 1/2 cosine 4 theta d theta. So we have the integral from negative pi over 2 to positive pi over 2. 1 plus 1/2 is 3/2 plus 2 cosine 2 theta plus 1/2 cosine 4 theta. Now, we have done both of these u sub integrals in this video specifically. So when they're in the same assignment, you don't have to do it again. You can just say, see problem number 5. So if you go back to screen number 3, in green, we did cosine of 2 theta. So I'm going to refer to that and not do it again. So we have 3/2 theta. We don't really need a parentheses in front of this 3/2. Plus 2 times, when we integrate cosine of 2 theta, we get 1/2 sine of 2 theta. Plus 1/2 when we integrate cosine of 4 theta, we get 1/4 sine of 4 theta. And all of this is from negative pi over 2 to positive pi over 2. I'm going to simplify these. See, I did need the parentheses. 3/2 theta plus sine 2 theta plus 1/8 sine 4 theta from negative pi over 2 to positive pi over 2. So let's plug these in. We get 3 pi over 2 times 3 over 2 times pi over 2 becomes 3 pi over 4, plus sine of 2 times pi over 2 becomes pi, plus 1/8 sine of 4 pi times pi over 2 becomes 2 pi. And then we have minus 3 over 2 times pi over 2 becomes a negative 3 pi over 4, and 2 negatives make a positive. And then we have minus sine of negative pi. And then we have minus 1/8 sine of negative 2 pi. Well, sine of anything pi is 0. So this is 0, this is 0, this is 0, and this is 0. So we end up with 3/4 plus 3/4 is 3 pi over 4 plus 3 pi over 4 is 6 pi over 4, which reduces to 3 pi over 2. And that is the volume we're asked to find. And if you look at this lesson, I think that you're pretty much set to do it based upon this video. I know it's a little bit shorter, but it's still, I think we've covered everything in it. So I hope you enjoy this lesson.